So here we're going to take a look at chemical reactions of triacylglycerols. Now, one category of reaction is hydrolysis reactions, and we've seen these before. And hydrolysis reactions are where we use water to break something apart. So the name here, hydro, tells us that there's going to be water involved. Now, this is the opposite of an esterification reaction, which we took a look at earlier. Now, when we do this, there's two different ways we can do hydrolysis with triacylglycerols. One is with an acid, and the other is going to be with a base. Now, when we do this with an acid, we're going to take our triacylglycerol we're going to be then reacting this with some acid. So maybe something like HCl, for example, but I'm just going to go like this. Okay, some acid like this. And then that is going to end up breaking apart this triacylglycerol and giving us glycerol and 3 fatty acids. 3 fatty acids. And the opposite of this, I shouldn't say the opposite, the other way that this could be done is with a base. Now with a base, we're going to take our triacylglycerol, we'll be reacting this with a strong base. Now this could be something like sodium hydroxide. It could be potassium hydroxide, just a strong base. And this ends up breaking apart this triacylglycerol into glycerol. And then instead of 3 fatty acids, we'll end up with 3 fatty acid salts. 3 fatty acid salts. And we'll take a look at both of these reactions here in just a moment.
A few moments later.
What we're going to do here is demonstrate the acid-catalyzed hydrolysis of the triacylglycerol below, or here. Now it tells us that this is acid-catalyzed, so that means we're going to have some acid involved. This is how we write acid, just a hydrogen ion. And then hydrolysis, that means we're going to be using water. We're going to be using water to break this molecule apart. Now a little bit about the structure of this molecule. These 3 carbons here and the oxygens here, this is the part, we might think of this as the backbone. This is the glycerol part here. And here you might recognize that you have a carbonyl group and then CH2 12. What this is this is just trying to show us that there's a long carbon chain here, but we're too lazy to write it out. It takes up too much space. We just kind of shorthand it by saying CH2 12. So there's 12 carbons plus 1 more, there's 13 carbons there. That's all. Okay, so we're going to take water, we're going to split this apart. And where we're going to split it is going to be right here, like this, and we're going to add a hydrogen to one side over here onto the glycerol side, and then the OH comes over here on this side here. So I'm going to redraw this and show what it looks like when the water molecules have been used to split this apart. So here what we have is these hydrogens have been added onto the oxygens here to create this structure, and this structure here is our glycerol. And then we're going to end up then with 3 of these here, these long carbon chains with hydroxides attached to them. So we're going to take these OHs and we're going to attach them on here. So it's going to look like this. We're going to have HO, carbon, double bond O, and then we're going to have the rest of this molecule here, which is going to be CH2 12, CH3. And we'll do that 3 times. Now that we've written this out 3 times, you might recognize these groups. We have an alcohol here on the glycerol side, and then on this side here, we have the carbonyl group and the hydroxyl group here, which gives us a carboxylic acid. So this is just going to be a long carbon chain with a carboxylic acid on the end. And we have a fancy name for these things here. So this is glycerol. This right here is glycerol. And then these 3 long carbon chains here, these are fatty acids. And we call them fatty acids because, like fats, they have long carbon chains, and then acids because they have the carboxylic acid group on there. For this problem, what we're going to be doing is the saponification hydrolysis with sodium hydroxide. Now, that's a lot of big words, but what we're going to do is we're going to take our triacylglycerol here and we're going to react it with sodium hydroxide. So for this one, I'm going to write out the sodium hydroxide. Sodium hydroxide, and there'll also be water in this one. Although the water doesn't actually get used in the reaction itself. Now, you might recognize the same basic structure from the last problem. And what we're going to do, just like the last problem, is we're going to split something apart here. In this case, it's going to be the sodium hydroxide. And we're going to add the hydroxyl groups this time over here. And then we're going to split these molecules right here, add the hydroxide groups to this side. And then on this side over here, this side, the fatty acid side, we'll add the sodiums. So I'm going to redraw this here. So there's our basic backbone of our triglyceride, or our glycerol. And we're going to have hydroxyl groups on here. And those came from our sodium hydroxide. And then we're going to have sodiums attaching onto our fatty acids. So I'm going to redraw these fatty acids here. There's one fatty acid. There's 3 fatty acids. Now, each of these oxygen atoms here are going to be electronegative, and they are going to be attracted to then these sodiums, which are electropositive. And you might recognize this or remember this as a fatty acid salt. So we have glycerol here and 3 fatty acid salts. We have a fancy name for these fatty acid salts, soap. And so basically what you're doing is you're taking the triacylglycerol, which is fat. This would be like animal fat, or could be plant fats as well. You're going to be adding a strong base to it, sodium hydroxide, and you're going to be creating glycerol and soap. And this is how soap is made. Now that we've had a chance to see how soap is made, let's take a look at how soap actually works. Now, there's actually a really cool story behind soap, and we'll get to that in just a second. So soap is, generally speaking, has this structure where we have the carboxylic acid, like this, oxygen, and then some zigzaggy, carbon string like that. And then here, this here is our carboxylic acid, but it's turned into a salt, so carboxylic acid salt. And that salt could be sodium, It's also oftentimes potassium. So it could be like potassium carboxylic acid salt here, or sodium. Now, so how does this stuff actually work? Well, if you ever got grease or oil on your hands and you try washing it, in the sink, it doesn't come off very well. And the reason for that is water is polar, and grease and fats and oils and such tend to be nonpolar. And if you remember back to like the first semester, maybe like dissolves like. So how do you get something that is nonpolar to dissolve in a polar substance like water? Well, this structure here, the carboxylic acid salt, when we add it to water, then the cation here usually dissociates, and you have this structure here that is very polar. Well, this end of it anyway is polar. And so I'm just going to go like this, and I'm just going to go right here and say this is polar. And so that likes to dissolve in water. And then this long tail here is nonpolar. Nonpolar. And we have fancy terms for this. This comes to us from the Greek. If it's polar, it will dissolve in water. So we say that this is hydrophilic. Hydrophilic, hydro meaning water, philic meaning liking. And then the nonpolar side here is hydrophobic. Hydrophobic, so water fearing. Now, that is helpful because this part here, the hydrophobic portion, would be attracted to grease, fats, and oils, and this part here would be attracted to water. And so if we were to take this and just kind of diagrammatically here, just because I'm lazy and I'm a chemist, I'm going to say that I'm going to draw it like this. I'm just going to say here's my hydrophilic end, and then I've got this long tail like this, okay? And so if I were to take a bunch of these and put them in water, then in water I would have a bunch of these hydrophilic heads being attracted to the water, and then the tails that are hydrophobic would be away from the water in the center like this. Now this has a fancy name for it. It's called a micelle. A micelle. And if you have a piece of fat, grease, or oil, okay, it could be attracted to the hydrophobic tails like this, and then those hydrophobic tails will form a micelle around it, and then that micelle will be soluble in water. And so if you ever wash your hands with soap or water, soap and water, and you have grease on there, you see that the water gets cloudy. And that's because of all of these micelles. Now, you might also be asking, what's the difference between soap and detergent? And I'm glad you asked that question. Okay, so this right here is a soap, all right? And a detergent, very similar structure, is going to have a phosphate group on there. So phosphate like this, OH, and then O like this, okay? And then the big long tail like that, okay? And so this right here could have, say, sodium or potassium like that. And so this, with the phosphate head as opposed to the carboxylic acid head, this makes it a detergent. Now, I told you there's an interesting story behind all of this. So there's a mountain in Italy called Mount Sopa, kid you not. And way back in the day, people used to do animal sacrifices to the gods because they wanted a good harvest or a date for prom or whatever. And so they would take the animals and they would get some wood, and then they would burn the animal and then pray to the gods. And somebody noticed that after it rained, if you washed your clothes at the base of Mount Sopa, your clothes got really clean. Now this part's a little bit iffy as to whether or not it's true, but it makes a great story. And what we know is if you take an animal which has fat in it, fat is a source of triacylglycerols, triacylglycerides, okay, triacylglycerides, and then the wood ash contains lye, which is potassium hydroxide here. So a combination of the animal fat and the strong base gets you soap. And then when it rains, the soap would wash down the river, and then people would wash their clothes, and their clothes would come out clean. And so this is a great story as to where soap came from, is Mount Sopa. Now whether or not that's totally true, I don't know, but I never let the truth get in the way of a good story. Another type of chemical reaction that can happen to triacylglycerols is hydrogenation. Now, hydrogenation is where we're going to be adding hydrogen to break double bonds. And so here I have a triacylglycerol, and I've got a couple of double bonds here. And if we were to hydrogenate this molecule, that is to say, let's add some hydrogen. So I'm going to just add hydrogen, H2. That H2 then will attack the double bond here and break it. And so what will end up happening here is if I take my double bond here and I break it, I'm going to just number these here just so I have, let's see, I'm going to go 1, 2, 3, 4, 5, 6, 7. Okay, so it's after the 5th carbon here, and we need a total of 7 in this fatty acid portion here. So I'm going to break this double bond here, and we just planting a seed here. Remember, nature likes cis double bonds because that's going to come back. So we're going to take this here, we're going to break this double bond, and we're going to go then 6, 7 like this, okay, and 6, 7, and we've added a hydrogen, and we've added a hydrogen here, and we've taken this fatty acid here and we've saturated it. And we would call this a saturated fat. A saturated fat. Now, why on earth would you want to do this? Well, there's a great reason. We've heard that taking our triglycerides, our fatty acids from animal sources, aren't so good for us for cardiovascular reasons. And so what if you could take something healthy like, say, vegetable oil, like olive oil, and turn it into a fat, a saturated fat? And this is exactly what they do, is they'll take a vegetable oil, they will hydrogenate it, and turn it into a saturated fat. That's what margarine is. Margarine is just hydrogenated vegetable oil, which sounds great, wonderful, right? It's made out of vegetables. That must be good for me. Yeah, but wait, there's a problem. When you hydrogenate a plant oil like this, sometimes these cis double bonds like this, they end up getting converted into trans. And so this right here may end up going like this, and we end up with a trans conformation. This becomes then a trans fat, a trans fat. And so it was found that this hydrogenation of vegetable oil was leading to trans fats. And remember, nature likes the cis conformation. So what does your body do when you get a trans fat in it? Well, the body doesn't know what to do with it. And so it starts to collect, and it might collect in your cardiovascular system, like in the walls of your arteries, and lead to atherosclerosis and cardiovascular disease. Okay, so they started first labeling foods that contain trans fats, and then they started banning trans fats. And so now I don't know if you can even get trans fats on purpose. You have to check your food labels for that. So that is hydrogenation, and how we can turn a unsaturated, like a vegetable oil, into a saturated fat and the source of trans fats.